weird. I'm not exactly sure what happened. I don't know. I didn't touch anything, so it just stopped, unfortunately. Oh well. We're taking a 10-minute break here. And then I'm on portrait, by the way. Okay, or whatever. Taking a 10-minute. Top chat, live chat. Damn. Jesus. Asparagine. Tiny mite on a short, tiny shell. Okay. Now let's see if maybe I can try. Okay, so this is the guanidium. So that's also ends. It's very basic. You can see it's positively charged. So arginine, ARG, R, very basic, a very basic polar, contains the guanidium group. Okay, aspartic acid, ASPD, side chain characteristics, negatively charged, very acidic. Aspartate. Yeah. Aspartic acid is the lower, shorter chain, and then glutamate or glutamic acid is longer chain. Did I get this? Yeah, I think I got it. Well, there you go. Glutamate, GLU, one letter name E. Side chain characteristics negatively charged. Acidic. Yeah. Oh, polar. Is it polar? I know, polar. On the beta carbon, isoleucine, One letter name. Isoleucine. One letter name I. Nonpolar hydrophobic. Oh, let's go. Valine, Val, V, nonpolar hydrophobic. Yeah, good. Tryptophan. The tryptophan has two wings. Spread two rings. Wings that spread two. Anyway, tryptophan. TRP, tryptophan. Tryptophan. Let me think. Tryptophan W. Definitely aromatic. That's what I got. Oh, nonpolar. Oh, yeah, okay, nonpolar. Yeah, nonpolar. Hydrophobic. Contains the indole group. Emits fluorescent light. Okay. Tryptophan, hydrophobic. Contains the indole group. Emits fluorescent light. I'm gonna go with asparagine. Asparagine. Hold on. Yeah, I'm gonna go with asparagine. Asparagine. Wait, no. Hold on. Yeah, is it asparagine or glutamine? I'm gonna go with glutamine. Glutamine, glue, Q, polar. Oh, let's go. Yeah. Yeah, asparagine is shorter. Glutamine is longer. I'm gonna go with tyrosine. Tyrosine, TIR. Tyrosine Y, and that's aromatic. Has this OH, so maybe polar neutral, barely polar. Okay. Precursor to catecholamines. Okay. Ooh, what the heck? Thinking leucine or isoleucine. I'm gonna go with leucine. Leucine, LEU, L, non-polar hydrophobic. Okay, I'm gonna go with asparagine. 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 Yeah, asparagine. What is asparagine? Is that? I think that's AS AS ASN N, and that's polar. Asparagine ASN polar. Yeah. Okay, good. Let's go. I'm gonna go with. I'm gonna go with histidine. 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 H. Basic. Oh, positively charged. Oh, neutral and physiological change. This one I'm gonna go with. I'm gonna go with. Phenylalanine, VF, aromatic. Yeah, obviously aromatic, hydrophobic. It looks like so nonpolar. Can absorb UV light. Okay. This is 309. 309. THRT. Polar hydrophilic. 309. Yeah, T polar uncharged. Good. I'm gonna go with. Oh man. I'm gonna go with serine. I think serine. Serine polar hydrophilic Sir S. Nah, cysteine. Dang it, man. What was serine? Oh no, serine was not. It was cysteine. Okay, and then serine. Serine zips with the straw with a hydroxyl tip. Cysteine curled sulfur strands. Cysteine curled her sulfur strands like golden hair. Sulfur strands. Serine sipped quietly through his straw tipped with dainty hydroxyl. Okay. Again. So. Okay, let me think. Lysine. Lysine, LISK, basic, positively charged basic, yeah. Okay. Oh, arginine, ARGR, basic, yeah. Positively charged. Okay. Really positively charged. Oh, okay. Yeah, there we go. Oh, positively charged. I need to add that. Yeah, okay. Positively charged. Contains the guanidinium group. Okay. Wow. Okay. I guess I shouldn't have added it. Well, that's okay. Cysteine, right? Cysteine plays with our sulfur hair. This is cysteine. Cysteine. Wait. Yeah. Cysteine. 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 C. Polar. Cysteine. C. Polar. Hydrophilic. Yeah. Cysteine. C-cis. Oh yeah. Cysteine C-cis. Yeah. Sorry. What is it? This is the amidoyl. Indoyl. Indoyl. That is the amidoyl. Oh, imidazole. Okay. This is the guanidinium group. Guanidinium found in arginine. Okay. We can do it, I guess. This is valine, val, V, nonpolar, hydrophobic. Okay, amino acids are simple organic compounds containing both a N-terminus and a C-terminus, a amino group, and a carboxyl group. Yeah, carboxyl group and an amino group. That's good. This is isoleucine. 3-letter name is 3-letter name is Ile. 1-letter name is I. Side chain characteristics, nonpolar, hydrophobic. Let's go. This is the. It was just there. This is the indoyl. Is it indoyl or indole? Indoyl or indole? Pronunciation. I think it's indoyl. Indole. Imagine it's indole.
Indole.
Okay, indole. Indole group found in tryptophan. Tryptophan is the owl with 2 wings and 2 rings. 2 wings and 2 rings. 2 wings and 2 rings. Double ring. Indole. This is the imizoil. Imidazoil. Indole. Okay, indole. Imidazoil group. Pronunciation. How to pronounce imidazole? Imidazole, maybe?
Imidazole.
Okay, that's the imidazole group. tryptophan, TRP, TRP aromatic, W psychiatric looks like it's actually so it's just aromatic, non-polar. Okay. Yeah, non-polar. Okay. Non-polar contains the indole group, emits fluorescent light. I didn't get that part. I can study it. I don't know. It's all good, I guess. This is the guanidinium group. Guanidinium. Found in arginine. Yeah, found in arginine. Arginine R, very basic. Arginine R, very basic, positively charged. That's good. This is glutamine, GLN, one letter. Oh, what the heck? GLN, glutamine. Oh, one letter Q, polar. Polar. Here you go. Polar hydrophilic. Polar neutral. Yeah, glutamine. Let's go. That is the that is the indole group. Yeah, tryptophan. Indole group, tryptophan. That is tyrosine, TIR, W. No. Wait. Y. Tyrosine, TYR, Y. Aromatic. Maybe slightly polar. Asparagine. 3-letter ASN, N. Polar, hydrophilic. Glycine. Stoichiometry that fucking anchors, except glycine is L. Stereochemistry. L. It's L. Left. Oh, what's the exception? 18 and 19 are S. Glycine is neither D nor L. All 19 proteogenic amino acids are L. 18 of the 19 are S. Cysteine is R. I don't know. Wait, you have to know this one? I don't know now. I technically got it right, but I didn't get the rest. Eighteen of the 19 are S except for cysteine. Okay, I guess that's good. All chiral amino acids except cysteine have a S configuration. Cysteine has L. Oh no, cysteine has R, S, R, S, and R. Cysteine has R. Right? That's what the other one said. All amino acids found in have the same solution. L with L cysteine. Oh yeah, actually yeah. So cysteine is in the R, 18 and 19 have S. Okay, sure. D amino acids or R amino acids also occur in nature. Sure, okay. L and D indicate L and D indicate stereochemistry. I mean, L and D indicate. Hold on. Yeah. What's happening?
Top on button. Be careful. Be careful. I mean, high slide.
No, it's not.
High slide.
It's okay, thank you.
Okay.
I don't know about this. Maybe I should watch the video. Oh man. I mean, it's kind of looking like tomorrow we'll end up doing the second and third sections. Ah. Oh. Yeah. Let's get it. I'm not sure. This card is fucked up. I'm not sure. Is it true? Oh. Okay. Um, wait. Lysine. Lysine. K. Positively charged. Polar. Wait. No, lysine basic. No, yeah, just lysine basic. Lysine LYS and K. Oh, this polar. Yeah. Wow. Cysteine. CYS. C. Polar. Hydrophilic. Green acids contain both an amino group and a carboxyl group. NH2, CO, COOH. Aminazole. Imidazole, found in histidine. Relative and absolute. Twitter ion. Indo, found in tryptophan. Zero. Oh, never mind. Pi equals to pKa of 1 plus pKa of 2 divided by 2. pKa of the amino group and the pKa of the carboxyl group when there is no side chain.
Layer here from layer cancel out to give me 0. Carboxy, the pH is much greater than the pKa, and the pH wins the proton for the solution, which means we take it away from the molecule. The carboxy group will be deprotonated for a charge of -1. If we add them up, we have +1 - 1 equals 0. So which is it? Is the pI going to be a pH of 7, or will it be a pH of 8, given that both of these pH values give us a net charge of 0? If an amino acid does not have an ionizable side chain, that means it only has 2 pKa values, one for the carboxy, one for the amine, then you simply take the average of the 2 pKa values, which is pKa1 plus pKa2 divided by 2. To find the pI for glycine, we add 2.3 plus 9.6 and divide it by 2. Remember on the MCAT you have no calculator, So we'll use the round up and down trick from the MCAT math series link below. 0, and the isoelectric point gives us an exact calculated value. That method is great when the amino acid has only 2 pKa values. But what happens if we have 3? For example, in tyrosine here, we have the carboxy and the amine that can gain or lose a proton, but we also have an ionizable side chain where the oxygen can lose a hydrogen. If we have 3 pKa values, do we average all 3? If we only use 2, which 2 do we use? Before I show you how to do this mathematically, I want to show you logically so that you understand where we're getting the values. Remember, to find the pI, we need to know exactly where the molecule is going to have a net charge of 0. If we compare the pH to the pKa values, you'll be able to figure out when it's protonated or deprotonated, and you can do the guess and check method, where you randomly pick a pH and determine what the charge is going to be. Or you can go through this logically. I'm going to show you how to write it out, but on the MCAT, you should be able to do this in your head. We're going to rank the pKa values from low to high. So we have 2.2, 9.1, and 10.1. Remember that when the pKa is greater than the pH, the pKa grabs the proton for the molecule. When the pH is greater than the pKa, the pH, the solution, grabs one from the molecule for the solution, meaning it's deprotonated. So if we were to compare what the molecule looks like in between the pKa values, you'll notice the trend. Start out by fully protonating the molecule and finding the charge. How do you fully protonate? You drop the pH well below the first pKa value. If the lowest pKa is 2.2, let's drop the pH to 1. At a pH of 1, every pKa is greater than the pH, meaning every group is protonated. So we get a hydrogen for a neutral charge, a hydrogen for a positive charge, and another hydrogen neutral. Fully protonated, we get a charge of +1. Remember the trick I showed you in a previous video, where as you raise the pH between pKa units, the charge goes down by 1, down by 1. If we raise the charge to the next in-between value, meaning above the first pKa, it's 1 and 0 for a net charge of 0. If we were to raise the pH greater than the next pKa value, in this case we have to go in between 9.1 and 10.1, for example, a pH of 9.6, we're going to get a half protonated deprotonated value for the 9.1 and the 10.1, but again, the trick is we drop the charge by 1, that's -1, and raising it well above 10.1. For example, pH is equal to 13, it should be -2. Let's prove it by showing what it looks like at 13. pH 13 is greater than 2.2. The pH wins 1 for the solution. We have a deprotonated carboxy with a charge of -1. pH 13 is greater than 9.1, so we deprotonate, get NH2, a lone pair but no charge. pH 13 is greater than 10.1, so we deprotonate the alcohol and get a charge of -1. If we add it up, we have -1, -1, and 0 for a charge of -2 as we predicted. How does this help us figure out the isoelectric point? Isoelectric point is the average of the 2 pKa values that are just before and just after 0. If the guesstimate here of pH 5 gives us a charge of 0, that means that when the pH is equal to the pKa at 2.2, we would expect to have the charge of +1/2. When the pH is 9.1 at the next pKa value, we would expect a charge of -1/2. And the in-between of +1/2 and -1/2 is 0. So if we take the structure in between those 2 pKa values, that is where we expect to see the isoelectric point. To figure this out mathematically, we simply say that the pI is equal to 2.2 plus 9.1 divided by 2. Remember, without a calculator, we're going to estimate. In this case, it's easy to add the exact values. 2 and 9 is 11. 0.2 and 0.1 is 0.3. Divide that by 2. This is difficult to do, so we can round this up to 11.4. 11 divided by 2 is 5.5. 0.4 gives me 0.2, and that means we have 5.7. If that was too hard for you, just round 11.3 up to 12, divide that by 2, and you get 6. Knowing that you rounded up, your answer should be rounded slightly down, and 5.7 is slightly less than 6. Many professors will teach you to simply take the two closest pKa values and average them. So I want to show you why that's incorrect. The two closest pKa values for tyrosine are 9.1 and 10.1. If we take the average of 9.1 and 10.1, we get 9 and 10, which is 19.2, and we divide that by 2. Let's estimate. Let's round it up to 20 divided by 2 is equal to 10. Let's see what happens to this amino acid at a pH of 10. pH 10 is greater than 2.2, wins 1 for the solution, we deprotonate and get a negative 1. pH 10 is 1 greater than 9.1, we're going to estimate that it's an exact protonation, deprotonation instead of looking at the buffer zone. 10 is greater than 9, deprotonate, win 1 for the solution, and that gives me a neutral nitrogen. And finally, at a pH of 10, 10.1 is close enough, we can put this at a buffer. So it'll be somewhere between negative 1 and 0, because it'll be an H or a negative, and that gives me negative 1/2. Keep in mind, we estimated, but we only estimated a little bit. And when we add these up, how to do it, let's see the trick when you're given 3 pK side chains, cysteine and tyrosine. If you protonate the R group that has a nitrogen, it's going to get a positive charge. And these refer to your basic amino acids, which include his one is high. Going to use on the book words.
Oh, okay.
PI is a
guanidium group found in arginine. L. Glycine. S. Is it the same thing? PI is equal to pKa1 plus pKa2 divided by 2. pKa1 is a carboxyl group. Relative and relative and something else. Okay. Absolute. pKa1 plus pKa2 divided by 2. A basic side chain. I'm not sure. Oh, okay. pKa2 plus pKa3 divided by 2. Same video. A basic side chain. A basic side chain. pKa2 plus pKa3 divided by 2. Relative, absolute. sweeter I am. Oh, acidic. I'm gonna say pKa1 plus pKa3 divided by 2. Okay. Gotcha. That's actually what I said. From the N terminus to the C terminus. pKa2 plus pKa3, maybe? Mm-hmm. C, COOH, H, NH, NH2, NH2HH. Right, okay. Alanine adds a methyl, so yeah, so I guess COO, COO, and then C CH3, NH3 plus, and the H. Mm-hmm. It's not really showing me anything here. Vowing forks. So we have the fork here. What has the methylene group and then it forks. Leucine. Leucine branches, but it doesn't branch at the beta carbon like isoleucine. And it branches, yeah, after that. Mm-hmm. So isoleucine is similar to leucine, but it branches at the beta carbon. So it branches first. It branch and then it continues the chain. Check mark. Methionine. Oh, methionine. Methionine. Oh, methionine. We're going to do 2 carbons. Caterpillar methyl will walk 2 carbons. We'll walk 2 carbons past sulfur, and then add a methyl at the end. He walks 2 carbons, passes sulfur gas, adds a methyl at the end. Contains a thiol group. When there is no side chain is P1 plus PK1 plus PK2 divided by 2. Same thing. N terminus to C terminus. That's going to be PK1 plus pKa 3 divided by 2. pKa 2 plus pKa 3 divided by 2. Relative and absolute. Glycine, yeah, so COOH, and then we'll have our alpha carbon, NH2, H, and then H on the left side as well. Non-polar, hydrophobic, not chiral. Valine will be the same thing, but then we're going to fork it with the carbon. So it's going to be C to another C, and then a go fork. So CH2, CH2, CH3. Oh, well, sorry, C and then CH2, CH3. Leucine will fork. Leucine will fork. Leucine will fork. We'll have 2 carbons and then a fork. Yeah, we'll have 2 carbons and then a fork. Alanine just have 1 carbon and you add the methyl. So C, CCH and then CH3. Yeah, CH3. Okay. Isoleucine will branch with a beta carbon, so we'll have C and then branch there, and then we'll do the fork. C will branch here, and then we'll. Oh, I guess they will just continue. Check mark. Sure. Methionine. We'll do CCS and then CH3. CCS. Let's go. Well, now we have to do high yields. Doing high yields, and then I don't know. Might be it for today, I guess. Tomorrow we'll get started on doing the 2 sections, and then we'll come back. We'll come back. Da, 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 da. We'll come back. We'll come back and do enzyme structure. What is this one talking about? I mean, sure, I'll hit it, but I'm not really gonna focus too much on it. And then I hit enzyme structure and functions, and we'll also hit enzyme kinematics. And maybe we can hit DNA. I really want to hit DNA at least. I should. We got 18. I don't know. I'm messing around. No, I'm just kidding. Worked out today. Almost finished the section, and I'm kind of behind, but we'll finish it. Finish Yankee. Review the structures. Good. Gonna keep hitting the Yankee. Getting the train started. I will take a break. I don't want to. My break to be eating, so I'm just gonna take an extra break.
Hello from the other side. Hello from the other side. Are you the mail? Hello? Anybody here? Hello? Why is this door being locked now? What's going on? Outside it says, welcome, please come in. Where's the key to the door? Huh? You don't have the key to the door? You have it? Oh, wow.
David?
Hello?
David?
Sleepy David? Hello? Anybody?
David?
It's too early to go night night. What's going on? Sleepy David?
Just messing with him. Gotta have some fun by yourself, you know? Like, come on. Joe Biden says, come on, man. Come on, man. Come on, man. Anyways, where am I at? All right, start the clock. So, well, we did today content review, structure review, and I'll finish up the Yankee cards, set us up better for tomorrow. Yeah, yes, sir. Yes, sir. Boom. Okay. Okay. I gotta watch the other video, by the way. Isoelectric point, and start figuring this stuff out a little bit better. Yeah, I'm not sure, but find a net charge for all these stats. 1 blank. Focus on trends like amine termini. Find the net charge for all these stats. Focusing on trends like amino termini and carboxyl termini. Memorize histidines, pK6 due to its proximity to the typical MCAT pH values. Identifiable ionizable groups. Identify ionizable. Determine pK values focusing on trends like amine termini. pK is around 911 and carboxyl termini pK is around 2. Memorize histidines, pK6 is proximity to the typical MCAT pH values. I don't know, probably again, I think. The net charge of an amino acid is the sum of all charges on its ionizable groups, including the amino group, the carboxyl group, and the side chain R group. Okay. Secondary structures of these stabilizers. Proline is known for breaking alpha helixes and being very rigid and flexible. And being inflexible. Proline has its own cyclic structure. Being rigid. No, well, is that rigid? Being inflexible. Okay. Glycine is its tiny size and achiral nature leads to rotation. Oh, glycine leads to rotation. Oh man. Disrupting. Known for breaking alpha helixes, disrupting. 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 I don't know. I'm not sure. Oh, breaking alpha helixes and being in beta turns. Disrupting alpha helixes. Okay, yeah. Each codon is a 3-letter word made of a combination of 4 letters, nucleic bases. Adenosine, thymine, guanine, cytosine. In the world of RNA, thymine is replaced with uracil. Okay, that one's at least good. These codons tell the cell which amino acid to start And to add, these codons tell the cell which amino acid to start next when making a protein. For example, the codon met. The codon, no. The codon AUG. Well, yeah, the codon methionine. I think it's AUG. Yeah, let's go. Let's go. Let's go. Let's go. Still got some of that knowledge. Don't forget it. Just don't forget it sometimes. Just don't forget that knowledge. Like your biology knowledge, just don't forget it. Oh, it's methionine. Hey, look at that. Good. Oh, when mistakes happen, mutations and their effects. What was that? When mistakes happen, mutations and their effects. Sometimes errors sneak into the genetic code, which are called wobbles. These can change the genes. Oh, codons. Okay. Oh, mutations. Yeah, mutations. I said wobble. Mutations can change the codons in the DNA, lead to the wrong amino acid being added to the protein, which can alter the protein's function. It's like a typo in a recipe that tells you to add salt instead of sugar. Your cake wouldn't taste very good. Mutations vary in impact. Some might not change the protein at all. It's still about the same amino acid. Other mutations can create a stop codon to really cut the protein short. Diseases, sometimes they might not have any noticeable effects. Okay. I got 8 plus 20. It's kind of weird, strange. Peptide bond is formed between the peptide bond. The peptide bond is formed between the peptide bond. The peptide bond. It's formed between the carboxyl group of one amino acid to the amino group of the other acid. Act as the, I don't know what you're trying to say here, buddy. The amine group nitrogen amino acid that's being added, which acts as a nucleophile. Peptide bond is formed between the amine group nitrogen of the amino acid is being added as a nucleophile, and the carbonyl carbon of the amino acid, the carbonyl carbon of the acid you have already had. Which, as carbonyl carbons often do, they act as an electrophile. Let's go and take a look at that. I vaguely remember that, no, Kim? I wonder if there's like a pretty good video. Oh, there we go. Let's watch the OChem tutor guy. He's not bad. He's not bad. Hold up.
And how is it different from an electrophile? So what do you think nucleophiles are? A nucleophile is basically usually has a lot of lone pairs or has a negative charge, and they basically love the nucleus. So examples of nucleophiles would be iodide. It has a negative charge. Water can behave as a nucleophile. It's attracted to the nucleus, which usually bears a positive charge. Some other examples of nucleophiles include hydroxide, that can behave as a nucleophile. Ammonia, that's another nucleophile. Electrophiles usually bear positive charges. They seek out electrons. They love electrons. So H plus is an electrophile. Fe3 plus, that's another one. A carbocation is an electrophile. Some other electrophiles may not have a positive charge, but they can accept a pair of electrons. So BH3, FeBr3, AlCl3, all of these can form a bond. They can accept a pair of electrons. And so an electrophile is basically a Lewis acid. A nucleophile is basically a Lewis base. Now, when dealing with the reaction mechanisms between nucleophiles and electrophiles, when drawing the arrow, it's always going to flow from the nucleophile to the electrophile. The arrow represents the direction of the electron flow. So it's going to travel from a region of negative charge to a region of positive charge. So let me give you some examples. Let's say if we were to put hydroxide with a methyl carbocation. We know that opposites attract. Hydroxide is going to donate a pair of its electrons to the carbon atom. And so we're going to get methanol. And now the oxygen has 2 lone pairs as opposed to 3. Now let's say if we had BF3. It doesn't have a positive charge, it's neutral. And so this is going to be the electrophile. And let's react it with a nucleophile, in this case, fluoride. It's electron rich, it has a lot of lone pairs. And so the nucleophile is going to attack the electrophile. And so this is a typical Lewis acid-base reaction. And now the boron carries the negative charge. Now here's a question for you. What about a ketone? Would you say it's a nucleophile or would you say it's an electrophile? Think about it. I'm going to give you a few minutes to find the answer to that question. Is a ketone an electrophile or is it a nucleophile? Technically, it depends on what is attacking it or what's around it. Under basic conditions, the ketone tends to behave more as an electrophile. Under acidic conditions, it tends to behave more as a nucleophile. Now, the reason why it can behave as both is because if you draw the resonance structure of this ketone, you'll see that it has a region that's nucleophilic and a region that's electrophilic. So if we take this pi bond and move those 2 electrons to the oxygen atom, we're going to get this resonance structure. And so the oxygen is going to carry 3 lone pairs now, and it's going to have a negative charge. The carbon atom has a positive charge. So as you can see, the carbon atom of a ketone, that is electrophilic. It bears a partial positive charge. The oxygen atom bears a partial negative charge in its original form. And so the oxygen part of the ketone is nucleophilic. The carbon part is electrophilic. So for example, let's say if we reacted a ketone with a nucleophile, such as I'm going to use hydroxide. Hydroxide can donate one of its lone pairs, causing this pi bond to break, giving us this tetrahedral intermediate. So in that one step, hydroxide acted as a nucleophile. The carbon atom of the ketone acted as the electrophile. Now let's react the ketone with an acid. So let's use H+, because clearly we know that H+ is going to be the electrophile. And so the ketone has to be the nucleophile. So the oxygen part of the ketone will attack the hydrogen, and so we're going to get a protonated ketone. And so now the oxygen has one lone pair instead of two, and it carries the positive charge now. And so in this case, that's when a ketone can behave as a nucleophile. So it can behave as both. So remember, the oxygen part of a ketone is the nucleophile, and the carbon part of the ketone is the electrophile. And so in this case, that's when a ketone can behave as a nucleophile. So it can behave as both. So remember, the oxygen part of a ketone is the nucleophile, and the carbon part of the ketone is the electrophile.
Glutamate, maybe. It's kind of similar. Disulfide pond. Is it sulfates or disulfide bond? I don't know. Oh, ionic. What can that be assumed of? Oppositely charged realizes. D and R. D and R. Aspartic acid, aspartate, and arginine, but not arginine, lysine, or glycine. And leucine. Hmm. Phospholipid bilayer. It expands the length of the phospholipid bilayer. Oh, expands the width. Oh yeah, I mean, expands the width of the phospholipid bilayer. Sign. Yeah. I'm sorry. Yeah, it's mostly water. makes sense. Oh, gotcha. Gotcha. Makes sense. Okay. Makes sense. Oh man, it's crazy. Identify the pKa of the carboxyl group, the amino group, and the R group. Calculate the average. I'm not sure. Calculate the average of the two central pK values. Okay. Ionic bonds. Ionic bonding and hydrogen bonding. Amino group, carboxylic acid, hydrogen group, and R group. Oh, NH3, COH, R group. Oh, that's pretty easy. Okay, you can go with this. The answer point is pKa 1 plus pKa 2 divided by 2. It's the exact pH value where an amino acid in gel electrophoresis plate. Within pH was stop migrating. Oh. condensation reaction. Peptide bond. Add phosphate groups. Oh man. T and E chemical. Oh, serine, 309, and tyrosine. Oh, that's right. Proteins are commonly phosphorylated to upregulate or downregulate their functions. Amino acids that can be phosphorylated include serine, 309, and tyrosine. Tiene que dar favorables. Heat can disrupt these bonds. Ribosomal unit. tRNA. Amino so tRNA synthase. Oh man. Amino acid tRNA synthase. Oh, synthetase. Synthetase. Proteins. Water. Codons. Hmm.
chemistry, hopefully we're comfortable with what it means to be an aromatic compound. Turns out there are some amino acids that are aromatic. And lastly, there's the it's intermolecular. Like we can create these charges. So if you're then we've got the R group here kind of reaches around and grabs onto the nitrogen. That's going to be a proline, right? And so that's what we have here. This is a proline. Then above that we have a lysine, and that's the protein. These are the same thing. You need to understand that the MCAT can give you either of these, and you need to be able to identify and what amino acid is. And going through amino acids, we understand how they're kind of put together. How is the MCAT likely to test this? Well, we'll talk about that. One way the MCAT can test this is by giving you a structure and asking you to identify the amino acids present. And this seems like a really overwhelming task the first time you get asked to do this. There's so much stuff going on, and students tend to panic. But remember, every time we form a peptide bond, we're going to have an amide. And we can kind of see there's like this chain kind of like going through everything here, and you can kind of see that there's a backbone to this. So if you ever find yourself lost, you can go and try to find like a specific region here where there is an amide. So that is a peptide bond. And so once you see this, like, oh, okay, well, we've got this carboxylic acid here, we've got our R group here, and we've got our nitrogen or amino group here. And so from there, it's easy to see, well, then that must be another peptide bond. And so we've got this one amino acid. It's actually glutamine with the 2 carbons and then the carbonyl attached to the amino group. And from here, it's easy to like kind of like just go through and just like, okay, well, carboxylic acid, R group, amine. Carboxylic acid, R group, amine. And so you can start to kind of go through and see where each of these peptide bonds is. And so you can kind of create and identify each one of these individual amino acids. Note that the MCAT could give you the structure the way this is, where they
Answer.
Huh?
could just tell you what the amino acid is. And they might do it with 1-letter symbols. For example, this first one here, it's got this wheel of
Arginine?
nitrogens, right? That's going to be arginine, the symbol is R. Then we've got the R group here kind of reaches around and grabs onto the nitrogen.
Proline?
That's going to be a proline, right? And so that's what we have here. This is a proline. Then above that, we have a lysine, which is K. We have another proline here. We have, next we have a glutamine, and then another glutamine. And then we have a phenylalanine, and then we have another phenylalanine. Then we got a real boring one. That's going to be glycine.
Glycine?
Then we have
Leucine?
leucine, and lastly we have
And then we have, what is that?
That's methionine.
Oh, methionine. Yeah, I see it.
So the MCAT could give you either of these. They could give you the structure and ask you about it, or they could just say, here's the protein, RPKPQQFFGLM, and that's the protein. These are the same thing. You need to understand that the MCAT can give you either of these, and you need to be able to identify and understand that they're the same thing. Another thing that I'll note here, this is just a great visualization, that if you look at that general shape of this protein, note that it kind of bends here. This bend here, proline. This bend here, proline. It's a good indication of showing you what's going on with proline as it induces kinks in a protein chain. So is that it? Are we just going to be asked to identify amino acids? Well, not exactly. The MCAT can start to do some really weird things about identifying how mutations can affect a protein. So we'll talk about that. When asking about the effect of mutations on amino acids, the MCAT will use some specific nomenclature that for a lot of people is going to be very foreign. That you might see something like they talk about this mutation. Let's say they say this mutation is a P17K mutation. Now, a lot of students are going to be like, I have no idea what that means. What that means is in our big long chain of amino acids, right, we have amino acid 16, we have amino acid 17, and amino acid 18 in this big long chain. Now, amino acid 17 was a proline, and the mutation has changed it into a lysine. So we did have a proline here, and now it's a lysine, which is K. This mutation is probably going to have some really big effects, because if we had a proline there, we probably needed that bend in the protein strand. Then we switched out proline, which is non-polar, for lysine, which is a charged amino acid. So we're kind of switching out two very different ingredients, and there's a good chance that that's going to break a lot of things. There's also really interesting mutations. Let's say we had a mutation that was S18D. Now, S is serine, 18 is the number of the amino acid that is mutated, and D is aspartic acid. So the amino acid 18 in this protein, we change from serine to aspartic acid. So let's say that we had this protein here, and let's say that there was glutamic acid here. Just this is what's going on in the protein. And let's say that this is this serine that we're talking about. And so this is going to have an OH. Now, we talked about how amino acids serine, threonine, and tyrosine can be phosphorylated. So we might come in here and we might phosphorylate this protein, which is going to give it a negative charge. Now, glutamic acid is already negatively charged, and it's always negatively charged. So these amino acids, like the glutamic acid and the phosphorylated serine, are going to repel each other. And so we might see that this protein changes conformation. Let's say it's opening up its active site because now we have this negative charge here, and those are going to repel. It's going to open the mouth of the enzyme or protein so that it can actually work. And this is why phosphorylating proteins can activate or deactivate an enzyme, because it actually changes the conformational structure. Now, with this mutation, right, we had serine at position 18 that we changed into an aspartic acid. So this serine is no longer a serine, it's something else. It's an aspartic acid. And we can't phosphorylate an aspartic acid, so we can eliminate that. But note that aspartic acid is a negatively charged amino acid. And it's always negatively charged, like all the time, just like glutamic acid. And so as a result, this protein, these charges, will be repelling each other. So this protein, you can't turn it on or off. It's always on because the negative charges have opened the mouth of this enzyme. This mutation is a mutation that is mimicking the phosphorylated state. It's a phosphomimetic mutation, phosphate mimicking mutation. The MCAT could throw this at you in a passage, and they need to know that you understand that, this mutation here is one that's going to mimic the phosphorylation state. And that's something that a lot of students haven't seen. So as you can see, the MCAT can test amino acids in a lot of crazy different ways, like talking about individual mutations, strictly identifying the properties of an amino acid, or even identifying from a big structure. need to make sure that you are ready for it because, as I mentioned, amino acids are the highest yield thing in the MCAT.
Oh, okay. All right, yes, gonna call it. I'm gonna have to do the deck tomorrow.